And maybe we'll start out of order execution, but we'll see. OK, and these are the feedback forms. Do you guys remember that? I'm happy to collect them, or we can collect them at the end also. Justin is ready to collect them right now, which is fine. But if you're willing to give them any other time, we're more than happy to accept them. Actually, any other time during the course of the course, we'd be happy to get your feedback. This is a fast-moving course, as you expected, hopefully, because that was what I said in the first lecture. But hopefully, you're learning a lot. But it's still good to get your feedback so that we can adjust some of the pace. And you probably noticed that we've been having a lot of lectures. Like, we've had only one recitation so far, but toward the later parts of the course, where the labs will get harder, we'll have fewer lectures and more recitations. Right now, if you think the labs are harder, they'll get a little bit harder toward the end. Or maybe easier. You're just getting started right now. But conceptually, they'll get a little bit harder. OK? All right, let's get started. We're going to talk about state maintenance and recovery, which we started last time. But you know that your homework 3 is due February 25th. And you know that your lab assignment 2 is due today. And lab assignment 3 is actually out too. It's due Friday, March 1st. And you're going to do a pipeline MIPS implementation in Verilog. So this should be exciting. And this is also an individual assignment. Actually, all labs will be individual assignments. There will be extra credit. Extra credit will be easier than the past lab. You won't have to do a completely different implementation. But you're going to optimize your pipeline MIPS implementation. And the goal is to minimize the execution time. Now, minimize the execution time on programs that you do not necessarily know. Because we're going to test your implementation on our own programs. Of course, you will design your own test cases. But this should be fun. Basically, this should be a balancing act in terms of cycles per instruction, average cycles per instruction, as well as cycle time. Hopefully, you'll like it. And you will get significant extra credit. The handout says up to 20% of the lab itself, which is 1% of the course grade. But I'm willing to be flexible to the top students. OK? OK. It'll be fun to optimize the pipeline. Even if you don't do it for extra credit, do it for the fun of it. OK. Just a note on testing your code. Testing is actually critical in developing any system. You probably do a lot of projects, and you should really test everything very, very carefully. Don't use just the test cases we provide. You should basically, you're responsible for creating your own test cases and making sure your system works for all test cases. The cases we provide may not necessarily test all of those cases, but we're going to test your labs with other cases that may exercise some of the corner case behavior of the logic, which means that you should be doing your own testing. Right. Well, why? You may ask why. Why are you burdening us with this? Well, because that's how real life works too, right? In real life, nobody gives you all possible test cases, workloads, users, et cetera, beforehand. So that's what you learn here to do the testing is applicable in the future. In fact, if you knew all of this, then designing a microprocessor would be really easy, right? You perhaps memorize all possible cases and just give the answer, spit out the answer. But that doesn't work that way. Of course, that assumes that you're able to do that with low hardware cost. If there are too many test cases that you need to memorize, then it's too much. OK. Feedback sheet. This is just a reminder. Some of you have turned it in. It's due today, but turn it in even if you're late. And if you do not have the feedback sheet, if you did not pick it up in the last lecture, it's online. Right. OK. Readings for today. You're already familiar with it. Today, I'm going to mainly cover this reading, implementing precise interrupts in pipeline processors. And the reading itself is actually nice. It talks about what I'm going to cover in a little bit more detail. But last lecture, hopefully you remember all of this, we wrapped up control dependence handling. We talked about a lot of different issues, predicate execution, wish branches, multipath execution, and prediction of different types of branches, calls, returns, indirect branches. And we briefly talked about that mux, the latency issues in branch prediction, right? Remember that next fetch address mux that has lots of inputs, and the inputs come from many different places in the pipeline? That's actually a critical part of the pipeline. We talked about interrupts and exceptions and the differences between them. I'll let you remember that. And we started talking about reorder buffer as a state maintenance recovery mechanism. Today we'll continue that, and we're going to probably begin out of order execution. But let's remember the state maintenance part. So when does this become a problem? In the 5-stage pipeline, we don't have a problem preserving sequential semantics, right? Because the result of an instruction is written at the end of the pipeline. But if you have something like this, if you have multi-cycle execution, what might happen is some operations can take longer than some younger operations that take shorter. And if these younger operations update the register file state earlier than the older operations, you're now violating the sequential semantics. Because if an older operation now generates an exception, the register file itself is in an inconsistent state. But we do want to keep the sequential semantics. We do want to have precise exceptions because of the reasons we discussed earlier. I'm not going to go through that, but I'm going to review the precise exceptions interrupts. What does that mean? Well, it means that the architectural state of the machine should be consistent when the machine is ready to handle an exception. All previous instructions should be completely retired, and no later instruction should be retired or should have updated the architectural state. That's what retire means. And you'll hear commit also. Commit means an instruction finishes and updates the architectural state. Some people also use graduate here. Retire, commit, graduate. These are all the same terms. OK. So what is the solution to this? Basically, we want to ensure that this happens, regardless of whatever is happening in the machine. Exceptions, interrupts, normal execution, speculative execution, branch prediction, load value prediction. We want to ensure that this is correct. At the boundary of an instruction, right? We do not want out-of-order updates of the state. So how do we do that? Well, there are 4 solutions we're going to cover. The first one, I've already given you the key idea. And we're going to look at advantages and disadvantages of each. And as I told you, existing processors use reorder buffers. They use future register files in a different way. And they use checkpointing also. So they use combinations of these solutions. OK, the reorder buffer idea was you can complete the instructions out of order in that multi-cycle execute pipeline. Different execution units can complete instructions out of program order. But before writing them into the register file or before making the results visible to the architectural state, we're going to reorder the instructions such that the sequential order is preserved. Simple, right? Very simple, actually. Basically, you have a reorder buffer that keeps instructions in order. And I've drawn you the picture. Whenever you decode an instruction, you reserve an entry in the ROB, reorder buffer. And that's a sequential entry. You basically allocate from the tail of the reorder buffer. When an instruction completes, it writes the result into the reorder buffer entry instead of writing directly into the register file. Remember, you can see that this path is not present anymore. You don't write to the register file. And when the instruction is oldest in the reorder buffer, which means that now it can update the architectural state, its result is moved from the to the register file from the reorder buffer or to memory. That's how memory updates also happen. OK, it's simple. And I've shown you this picture, what's in a reorder buffer entry, and you can think about what is required to keep in that reorder buffer entry to ensure these sequential updates. And remember that we need to keep the program counter in case we want to recover from exceptions. And in fact, in your pipeline also, you will need to propagate the program counter with an instruction, right? Even though you may not need it. But at some point, you may get an exceptional condition, which means that you will need the program counter to somehow restore the state. OK. So if you look at the pipeline, now what happens is we don't update the architectural state when this second add ends. We write its result into the reorder buffer. And that instruction now moves out of the pipeline. And it keeps waiting in the reorder buffer. And the reorder buffer has a finite state machine that keeps checking, is the oldest entry ready to retire, ready to update the architectural state? Well, until this first floating point multiply writes its result into the reorder buffer, that answer is false, right? Because this floating point multiply is still in the pipeline. That has an entry in the reorder buffer. That's the oldest instruction. So if you look at the reorder buffer, you have an oldest pointer, and you have a youngest pointer. And this is a circular buffer, right? Oldest pointer has floating point multiply and state associated with it. That's the first one. The youngest one is whatever is the bottom one. But the second one is the floating point add that caused our problem in our previous picture. And there's a bit that says completed. That's a big bit, but it's a bit. In this case, it is completed, but this one is not completed. For example, in any of these cycles, the state looks like this for the top two entries in the reorder buffer. But when this floating point multiply writes its result into the reorder buffer at the end of this cycle, this completed bit gets set. And in the next cycle, the finite state machine that's checking the reorder buffer checks if the top entry is completed, and the answer is yes. What that finite state machine does is it takes the result of the floating point multiply, takes the destination register ID of the floating point multiply, writes it into the register file, and deallocates the floating point multiply from the machine in that cycle. That's what that write result cycle is now. Take the oldest instruction, write its result into the register file or memory, and get rid of the oldest instruction from the pipeline. Make sense? It's pretty simple. And in the next cycle now, floating point add can retire with the same mechanism. OK. So one question is, here, this floating point add is executing. It has executed, and it has its result available, written to the reorder buffer. What if some other instruction that comes later needs that value that's in the reorder buffer? Right? The value is not in the register file because this floating point add did not write into the register file yet. The value is sitting here. We would like to make that value available, right? To that. Otherwise, we need to stall somehow. Well, one solution to that is, but we don't normally read the reorder buffer. Reorder buffer is actually for state maintenance, right? For in-order updates. But if we would like to read that value, somehow we need to read the reorder buffer. And the idea is to read the reorder buffer in parallel with the register file at this decode stage. Make sense? Now this is going to add some complexity to our pipeline. So that's what our pipeline would look like now. You write the reorder buffer. When an instruction finishes, it writes the result into the reorder buffer. And when a later instruction comes, it checks for its value in the register file and the reorder buffer. Right? So if this floating point add, let's say it was writing to register 5, what would the register file look like? Register file would have a valid bit. Let's say you were using scoreboarding. Is that register 5? I'll just single out register 5. This register 5 is invalid because the value is not in the register file because this floating point add was writing to it. Right? We've scoreboarded that register 5. But the value is in the reorder buffer. How do we know? Because reorder buffer looks like this. We have the destination register ID, and we have a bit saying, is the destination register ready? And we have destination register value. This is destination register ready is the same bit as completed that I've shown you here. Basically, has the instruction completed. Finished execution and written its result into the reorder buffer. And we have this oldest. And we have a valid bit for each entry in the reorder buffer that says, is this entry in the reorder buffer valid? And we have the youngest. So if you look at the floating point multiply, it sits here. And I guess at this point in time, when it finishes writing its result in the register file, it's already valid. It was allocated. Its destination register is ready. its destination register ID is register 5, and it has produced some result, let's say 1,000. And this value is sitting here for the next 1, 2, 3, 4, 5, 6, 7 cycles, right? If another instruction comes in, I don't know, a multiply, that sources R5, we'd like to supply this value. This value is nowhere else in the pipeline because the instruction finished, right? It's not in the register file because we don't want to update the register file, but it's somewhere here. So how do we supply that value? Well, okay, ignore that bypass path for now. How do we supply that value? Well, we need to somehow search the reorder buffer, right? Because how do we do that? We take R5 and index into the reorder buffer. It's not that simple, right? Here, the values, you have a nice register file, and you can index directly into register 5 and get the value. You can decode the address. Here, where is R5? You don't know, right? Well, you need to search. So there's a content-associative search now. Because you don't know which instruction is writing R5. Because the indexing into the reorder buffer is not done based on the register value. It's basically a sequential list of instructions in the order they were fetched. So this search is actually expensive. Basically, you need to take the source register value and compare it to all of the destination register IDs of valid reorder buffer entries. That's the idea. And it's not as easy as that, actually, because there may be multiple instructions writing to register 5. Right? Remember right after write hazards? Actually, this is or dependencies. We have actually eliminated those right after write dependencies by having a reorder buffer. We'll get to that. But there may be multiple instructions here. Another instruction may be writing to R5 also, a valid instruction. You really need to get the youngest value of the R5, right? From the instruction that is writing to a register file, the last. So it's a content-associative search, but it's a little bit more complicated because it's really age-based content-associative search. So this is a tough thing to do. We're going to try to solve this problem. But we do want to bypass this value. Otherwise, you'll incur additional stores. OK. So you need this logic, which is actually the downside of the reorder buffer. Well, you do need other bypass paths also, right? So there may be an instruction that's issuing here, and you need to get the result. OK. So how do you fix this problem? I guess I've flashed you one possible solution. It's obviously not a good design because you don't if you have a content-associative search right here, you may be lengthening your critical path.
Because secondary register file.
Secondary register file.
Writes to, so if you're looking for R5, you just look for R5 in that one.
I see. That's good. We're going to fix it. You're jumping ahead. That's going to be. We're going to have another register file later on. That's the future file.
This one is just. So you just select each register. If you write to like R5 or something, I guess you select it underneath that box there.
That's right.
Okay.
Yeah. But I think your idea is similar. So without going into the secondary register file, one thing you could do is you could actually use some indirection, right? Because you actually know what is the instruction that's writing to the register file. You could keep the record of that. How do you do that? Well, you can access the register file first. Let's keep this here. And let's maybe move here. I guess we don't have a cleaner whiteboard today. What you can do is, we still want to have the reorder buffer. And we obviously want to have the register file. And we want to have the valid bit. What we can have is, with each register file entry, we can have a tag, or let's call it the reorder buffer ID, of the last writer to that register. Right. So basically, when this add comes in, floating point add comes in, it's writing to register 5. its valid bit becomes 0, and it's allocated in entry 1 of the reorder buffer. So it sets the tag of this register 5 as entry 1, saying that the instruction that's going to produce the value of this register actually it resides in reorder buffer entry 1. Make sense? So now R5, if R5 value is not in the register file, if valid bit is 0, now we can look up the reorder buffer entry that's indicated by the tag and check if the value is actually there. If the value is there, then we know that we can get that value, right? Is this clear? It's simple, again. We've used indirection now, right? And I guess basically what we've done is we've mapped the register to a reorder buffer entry. And this is actually one of the key things in renaming. We've really renamed this register, right? The register name is, at least microarchitecturally, renamed to the reorder buffer entry 1. Register 5 is not register 5 anymore. The value will be produced by reorder buffer entry 1. And if there's another entry, if there's another register, another writer to register 5, what it does is it basically changes this tag to, I don't know, maybe 58. Now this instruction that's at reorder buffer entry 58 will produce R5. That's the last producer of R5. And if an instruction comes in, when it gets decoded, it looks up reorder buffer entry 58 to get its value. Make sense? Yes?
But if those instructions keep coming out of order, how do we know that the one that was most recently read is the most recent value that we want to use?
Which instructions come in out of order? Here?
Yeah.
Yes, they don't come in out of order. If they come in out of order, yes, this doesn't work. Here, instructions come in order. Because you're fetching them, right? And then you're decoding them and you're accessing the register file right away. They should not come in out of order. Yes?
So in the pipeline, if there is an instruction which is going to update, say, R5, and it takes more stages, and the next instruction is going to take lesser number of pipeline stages, then previous one is not going to update this table until he finishes execution, right?
Which table?
This table.
It's the register file.
The tag. The tag is not going to update until he has finished execution.
Okay.
Right?
No, tag is updated when the instruction actually is decoded, right? Instruction is decoded, it accesses the register file, it's writing to R5, it sets the valid bit to 0, it allocates a reorder buffer entry, and takes the ID of the reorder buffer entry and puts it here. Let's get rid of 58.
It's going to be updated only once the execution is done, once the values
That's
are
right,
updated.
yes.
The next instruction could have a shorter time where it needs the value to execute.
Okay.
Right.
Then that instruction stalls here. When the instruction is decoded, let's say this is the add that's writing to R5. Let's say there's another add that comes right after that's sourcing R5. It's the same as the pipeline we've discussed, right? It's sourcing R5. It checks R5. Is the value here? No. The value could be in the reorder buffer entry. That's reorder buffer entry 1. Now the question is the value there. If this instruction is not finished yet, then this completed bit is 0. And that value is not there. This instruction stalls. Pipeline stalls. Right. Okay? Okay. Okay, well, I've described that basically. You access the register file first. If the register file entry is not valid, it provides you the entry of the reorder buffer that contains, or that will potentially contain, the value that's going to be produced. And then you access the reorder buffer next. Okay? And that value may or may not be in the reorder buffer. If it's in the reorder buffer, then you can get and execute. If it's not in the reorder buffer, you stall. We're still in order. We're still waiting for the result. OK, you've seen this already. I think you can think about whether it can be simplified further, but I'm not going to cover that right now. So what we've really done here is we've we can this way eliminate anti and output dependencies. Remember, I've given you this slide before, and we've actually looked at this tagging mechanism before without the reorder buffer. We're really renaming now a register that's in the register file to a register that's in the reorder buffer, because we have values in the reorder buffer also. And we have actually a lot of values here. We can store this register. Let's say this is a 16-entry register file. We might have a much bigger reorder buffer that's 128 entries, let's say. And R5 may be present in all of those 128 entries, right? If all the instructions are writing to R5. Basically, you renamed R5 to different locations into reorder buffer. Make sense? OK. And you've seen this. Basically, the register ID is renamed to the reorder buffer entry that will hold the register's value. This is also called the architectural register ID. You can think of these values that are stored in the reorder buffer as physical registers, right? They're not visible to the architecture. This is purely microarchitectural. So you can think of these as physical register IDs, the reorder buffer entries. And after renaming, reorder buffer entry ID is used to refer to the register. And we're going to extend this later on when we do out-of-order execution. We're not even going to stall this instruction that comes later. We're going to use this ID to actually link the producer to the consumer. The consumer will take this ID and say, I just need this register that's at reorder buffer ID 1, or some name 1. And at some point, when somebody produces that value, they're going to broadcast this tag. And if I see this tag broadcast, I know that my value is ready. Yes?
How do you decide how big to make the reorder buffer?
Oh, that's a good question. Let's defer that for later. Because we're going to look at an out-of-order pipeline also. That will depend on how much look-ahead you want to have in your system. But in an in-order pipeline, it will depend on how long your how long latency some of your operations are. But that's a good question. I mean, it will change in an out-of-order pipeline. OK. So basically, this way, we can now eliminate anti and output dependencies. We don't need to stall on them. We can have many different versions, if you will, of register 5 in the reorder buffer. And this is how you get the illusion that there are a large number of registers, right? For the compiler, there are few registers. These are architectural. So it can have all of these false dependencies. But the hardware gets rid of those false dependencies now, right? Because you have many, many registers internally. OK. OK. I guess let's wrap up reorder buffer. So how does this work in the end? At decode stage, the instruction accesses the register file and the reorder buffer. And indirection is probably a good way of accessing it instead of doing it in parallel. We do it serially. Of course, this does lengthen the pipeline a little bit, right? If you don't get the value from the register file, you need to access the reorder buffer. At the same time, the instruction allocates an entry in the reorder buffer and writes its tag to the register file, to the destination register in the register file. The logic checks if the instruction can actually execute. That's the dependency check logic now. If so, we dispatch the instruction. Dispatch is a term I'll introduce, I guess. Dispatch means you send the instruction to an execution unit. And unfortunately, in computer architecture terminology, some people use dispatch in some other way. But let's assume that dispatch means instruction is sent to the execution unit. At the end of the execute stage, instructions now can complete out of order. An older instruction, a younger instruction, can take much shorter time than an older instruction. And now you can have variable latency, right? Loads and stores can take hundreds of cycles here. And in the meantime, you could be executing independent independent adds and multiplies. But remember that we're still sending these instructions, dispatching the instructions in order. we're going to change that later in this lecture. So instructions are sent to the execution units in the order they're fetched and decoded. Completion, when an instruction completes, it writes its result to the reorder buffer. It doesn't write to the register file. And when an instruction is ready to retire, which means that it's the oldest instruction in the machine, we check for exceptions. If there are no exceptions, the result is written to the architectural register file or memory. Otherwise, the pipeline is flushed, and we start from the exception handler. And you can, I'll flash forward a little bit. This is the same as a branch misprediction also, right? When you have a branch misprediction, it's like an exception. And this is how you recover the state. What happens is when a branch is ready to retire, you check if it's mispredicted. If it is mispredicted, then you flush the pipeline and start from the correct next program counter as determined by the branch's resolution. So we're going to use the same mechanism for branches also. And we're going to see some issues related to that later on. So basically what we've done is an in-order dispatch pipeline, or in-order schedule pipeline, or in-order execution pipeline. But instructions can complete out of order. They cannot start execution out of order at the beginning of the execution units, but they can complete out of order. And we do retirement in order to preserve sequential semantics. OK. So what are the trade-offs with the reorder buffer? Advantages, it's conceptually simple for supporting precise exceptions, right? You basically reorder things such that you are sequential in the end. And it can eliminate false dependencies, as I described here, right? Disadvantages, well, this is the biggest disadvantage, actually. This reorder buffer needs to be accessed to get the results that are yet to be written to the register file. You either use a CAM, content addressable memory, in the reorder buffer, which is complex, or you use indirection. Either way, you have increased latency and increased complexity. Right? So can we get rid of that? So here you have increased latency and a lot of increased complexity because of the content addressable memory, especially if your reorder buffer is big. Here you have, well, sequential access, right? If your value is not in the register file now, you need probably one more cycle to access the reorder buffer. So can we get rid of that? And these other solutions that we're going to talk about actually try to get rid of that, eliminate this disadvantage. OK, let's talk about history buffer. Any questions so far? Yes?
It's possible to coalesce the reorder buffer.
Oh.
Like suppose.
What do you want to do by coalescing the entries in the reorder buffer?
For example, if you have a very long load at the very first entry, then none of the other entries can be retired.
That's right.
Suppose you have a long chain of dependency later on, and that long chain of dependency, you wouldn't need any of the previous instructions because they're already used, and so you need to like retire all of them.
I see.
As in
So they're already done, basically. You're thinking of a case where you have a long latency load here and a bunch of instructions that are already done because they were independent, but they're waiting to be retired. So you want to somehow collapse them.
Yes.
Well, you could imagine, right? If you're the architect, potentially you could do something like that, actually. Existing designs don't do that, but potentially you could do something like that to save space in the reorder buffer so that you can fetch more instructions. And I'd encourage you to think about it. Yes?
Would that be just made up as a system? Because that would be a variable number of things per cycle. So.
That's right. As long as you ensure that they don't cause any exceptions, basically, in the next cycle, what will happen is you somehow update a lot of registers at the same time, if you can design the logic to do that.
And most of the time, the reorder buffer is probably doing nothing, right? Because it's waiting for data to come in.
That's right. It's waiting for the oldest instruction to be ready.
Right. So then the reorder buffer most of the time have extra cycles to do all of the coalescing.
That's right. I like the way you think. Existing machines don't do that, but there are potentially ways of doing that as long as you keep it simple. OK, let's take a look at another solution, history buffer. Here, the approach is a little bit different. So what was the problem that we were having here? The problem is the new value is not available to us right away, right? The new value that's produced for a register we need to somehow find it. We need to search for it, right? Here we were searching it through content addressable memory. Here we have indirection to search it, to find it. History buffer says, well, I'm going to update the register file when the instruction completes. So directly, when the instruction completes, it updates the register file. But I'm also going to record what was in the destination register before I updated it. And if there's a problem later on, like there's an exception, if I need to undo I will undo my update. I'll take the old value and restore it into the register. So in a sense, this is more optimistic, right? Reorder buffer was pessimistic. Pessimistic in the sense that it's not writing a value into the register file until we know that the instruction really can be completed. Whereas history buffer, optimistic. I'm going to assume that I'm going to complete this instruction. So update the register file. If there's a problem, I'll undo my update. It's essentially a log. That history buffer is a log of old values. OK, it's simple, right? Conceptually also simple. But there are issues with it. So when an instruction is decoded, it reserves a history buffer entry. When the instruction completes, it stores the old value of its destination into the history buffer. So somehow you need to read that old value. And when the instruction is the oldest, and there are no exceptions or interrupts, the history buffer entry is simply discarded, right? You can get rid of the old value now because you know that that instruction can complete. And it did the right thing by updating the register file. The problem happens when an instruction is the oldest and an exception needs to be handled. So now you need to go through the history buffer and take the old values in the history buffer and write them back one by one to the register file, because you shouldn't have updated the register file with those values. You optimistically update the register file, assuming that there won't be an exception, but an exception happened. Right? So basically, you rewind the history buffer. Right? So history buffer actually looks similar to reorder buffer, but it's used in a very different way. Right? You have the oldest instruction here, and you have the youngest instruction here. And you store the destination register of each ID and the old value that was in the destination register before you clobbered it. And when the oldest instruction for some reason has an exception, you need to walk this history buffer from the youngest instruction to the oldest instruction. For each entry in the history buffer, you take the destination register ID and restore the old value. Next entry, take the destination register ID, restore the old value. Next entry, take the destination register ID, restore the old value. Until you come to the oldest instruction that caused the exception. Makes sense, right? And if the exceptions are not common, this may be a good solution, right? Because you do this once in a blue moon. A lot of work, yes. On an exception, there's a lot of work potentially. Depends on how long your history buffer is, of course, right? And this goes back to his question, how big should your look ahead should be, perhaps. OK. So, but there's an advantage, right? The advantage is now, when you decode an instruction, you get the register ID, source register ID. The value is always in the register file, right? Well, or in the bypass path, somewhere. You never need to access another structure to get the value. You either stall, or the register file has the value, or the bypass path has the value, forwarding path. You don't do this. There's no indirection. So it's quick, meaning register file contains up-to-date values. History buffer access is not on the critical path at all. Whereas before, reorder buffer access was on the critical path, regardless of whether we did a content addressable memory or an indirection here. And you see that we now have this path. At the end of the execution, the instruction updates the register file. The disadvantage, and of course, I'm glossing over some details, but an instruction updates the register file if its tag matches again, right? You could do renaming with the history buffer also. So you do need that infrastructure with tags. You don't want to have totally out of order updates in the register file, right? I'll let you think about that. But we're building upon the previous concept. So that those tags are still there in the register file, because you do want that latest value of the register, right? OK, so disadvantage, well, first disadvantage is you somehow need to get the old value. We didn't have this problem before, right? Normally, when you do an add, if your destination register is not the same as your source register, you don't need to read your destination register. Right? You just write to your destination register. So there's one issue here. The second issue is, as you've seen, you need to unwind the history buffer upon an exception. Now that exception or interrupt handling latency increases. And if you're doing this for branch mispredictions, branch misprediction handling latency also increases. OK. So we're going to solve both problems. But this is bothersome, right? If you really need to read the old value of your destination register, now your register file becomes complex too. Because you need one more port to your register file, right, to get the old value. OK. So the third solution, I think, fixes both of those problems. And the idea is to keep two register files. I think this is what you were getting at, perhaps. Keep two register files. One is architectural. You update in order, in sequential order. And the other is speculative. It contains the latest value whenever it's produced, as soon as it's produced. And we're going to call one file the architectural register file. It's updated in program order for precise exceptions. And we're going to use an reorder buffer to ensure in-order updates. We'll still have the reorder buffer, but we're not going to put it on the critical path. We're not going to get the values from the reorder buffer. We're going to get the values from the speculative register file, called the future register file. It's updated as soon as an instruction completes. And of course, again, if the instruction is the youngest one to write to a register. So the purpose of the future file is to have fast access to the latest register values, which was the problem we were trying to solve with the history buffer also. It contains speculative state. This is also called front-end register file in some existing processors. Like Pentium 4 had a similar concept. It didn't exactly have the register file itself, but it had pointers to this front-end state, speculative state. They called it the front-end register alias table. They had the pointers to the registers that contained this front-end register file. And architectural file is used for state recovery on exceptions or branch mispredictions. And this is also called the architectural state. This is also called the back-end register file, because it's really updated in the back-end of the machine. Back-end, if you think of the machine as fetch, retire, this is the back-end, and this is the front-end. OK? That's the idea. It's simple and beautiful, right? This is also called the retirement register file. Actually, Pentium Pro called it the retirement register file. OK, so this is how it looks like. Now we have a future file, which is updated when an instruction finishes its execution. When an instruction finishes its execution, it also writes its result into the reorder buffer, so that that result is later written to the architectural register file when the instruction is the oldest in the machine. The advantages, now you don't need to read the values from the reorder buffer. There's no cam or indirection. And as opposed to the history buffer, you don't need to have more than, well, you don't need to have an additional port into the future file, because you don't need to read the old value ever, right, of your destination. It doesn't work that way. The disadvantage, now we have multiple register files, right? But maybe it's OK. If you want to have fast access, there's no free lunch, right? You want to have fast access to the value that's as soon as it's produced. And you also want to have in-order updates. That's what you need. Okay. And this architectural register file is restored into the future register file only on exceptions. Basically, when an exception happens, this future file state is speculative now, right? You've already updated it with later instructions. But architectural file contains the precise state. So basically, all you need to do is to ensure that the instruction is the oldest in the machine. Now your state in the architectural register file reflects the state. Let's say you have this add that's oldest in the machine. Because architectural register file is updated, when the oldest instruction in the machine completes, now you know that before you retire this add, you're at a precise state in this architectural register file. All previous instructions have retired, committed, and no later instruction, including the add, have updated the architectural register file. So you can safely take this architectural register file and copy its state to the future file and restart execution. OK. Well, that's a disadvantage, but that's a necessary evil that you need to do. OK. So this is the final design, in-order pipeline with feature file and reorder buffer. When you decode an instruction, you access the future file. If the value is there, that's great. If the value is not valid, then you wait until the value is produced, or maybe the value comes from a bypass path. And you allocate, the machine allocates an entry for that instruction in the reorder buffer. Of course, checks if the instruction can execute. If so, it dispatches the instruction into the appropriate functional unit. In execute stage, instructions can complete out of order. When the instruction completes, it writes its result to the reorder buffer as well as the future file. It's not shown here. I guess I need to update these figures. But yeah, it writes its result to two places, reorder buffer and the future file. When instruction is ready to retire, the reorder buffer logic checks for exceptions. If there are no exceptions, the result is written, the destination register result is written to the architectural register file or the memory. Otherwise, the pipeline is flushed, and the architectural register file is copied to the future file, and we start from the exception handler or the next program counter. Again, this is an in-order dispatch machine. We're dispatching instructions in order. Instructions are completing out of order. Instructions are retiring in order again. OK? So how do you actually handle the exceptions? This is probably obvious. But when the oldest instruction is ready to be retired, and it has caused an exception, the control logic does some things. So how do you actually figure out it has caused an exception? In the reorder buffer entry, you also have a bit that indicates there is an exception that the instruction has caused, and this is the type of the exception. Maybe the instruction, when it executed, it was a divide by 0, right? You don't handle that exception right away. You wait until the instruction becomes the oldest. Right? Basically, the control logic recovers the architectural state. That's copying the register file into architectural register file to the front-end register file. Flushes all younger instructions in the pipeline, saves the instruction pointer and the registers as specified by the ISA, and redirects the fetch engine to the exception handling routine. Right? And you all know about vectored exceptions, for example. That's one way you can get the address of the exception handling routine. OK. So branch misprediction actually resembles an exception, right? I flash forwarded to this earlier, but it's essentially an exceptional condition. And it can be handled in a very, very similar way. Well, it resembles an exception, except it's not visible to the software. Right? We're predicting branches, and none of that is visible to the software. So how do you do branch misprediction recovery? It's similar to exception handling and can be initiated before the branch is the oldest instruction. But how can we do that? Because if you look at this pipeline, let's go back to this pipeline. If we handle it exactly the same way we discussed, the branch, let's say branch execution is very quick, right? Unless the branch is dependent on something else, but we're not doing out-of-order execution yet. The branch executes, and if you mispredicted the branch, you know the target address right away. But you still need to wait until the branch is the oldest in the machine, right? Because your state is kind of messed up. There may be instructions that come later that have actually updated the state. And your state is not fully correct, right? Because there may be instructions that are earlier that are not retired yet. You have this branch here. Well, I guess I'm going to overwrite the history buffer. There you go. In case you need that information. Why do you need to wait until the branch becomes the oldest? Because if you look at your reorder buffer, this is the oldest instruction. This is the youngest. And you have a branch somewhere in the middle. The oldest instruction, let's say it's a load, is not complete yet. Not complete, 0. Branch has completed, and you know that you've mispredicted the branch because you've executed it. But you cannot redirect the fetch engine right away. Why? because you have this future register file here that doesn't have the correct values, right? That has all of these junk values here. Make sense? And future register file perhaps doesn't have the values that you need here. So you need to wait until the branch becomes the oldest, such that you have the correct state to execute the next instruction in your branch, after your branch. So we're going to try to solve that problem. OK. But all three state recovery methods can be used, actually, for branch misprediction recovery. When you get a branch misprediction, you can rewind the history buffer also, right? When the branch is the oldest in the machine. But there's a difference. There's a big difference between exceptions and branch mispredictions that prompt, or that should prompt everyone to handle these differently. Anyone can think of what that is? Yes?
You know that there could be a branch misprediction the moment you fetch the branch. So you know beforehand from where you should start thinking of like waiting.
I see. That's right. That wasn't the difference I was thinking of, but you're right. You're right. You know the next path, so you can handle it in some other way that we discussed earlier. But let's assume that you're just predicting the branch. Think about how frequent these things are. Which one is more frequent? Hopefully branch mispredictions, right? Hopefully you're not getting an exception every 1,000 instructions, let's say. Whereas you could easily be getting branch mispredictions every 1,000 instructions. Think about 1,000 instructions. Let's say 100 of them are branches. That's low, actually. 10% of them are branches. And let's say your branch prediction rate is 99%. Branch prediction accuracy is 99%, which means that you get one branch misprediction every 1,000 instructions. That's very, very frequent. And if you actually need to wait until the branch becomes the oldest instruction in the machine, you'd be waiting for a while, right? Assuming your reorder buffer is, let's say, 128 entries, which is not unreasonable. Pentium 4 had 126 entry reorder buffer. And you can imagine, maybe you can imagine why it's 126. I'll let you answer. But the quick answer is basically it had reorder buffer using the micro operations. And it was able to retire 3 micro operations per cycle. So it stored 3 entries. And 126 is divisible by 3, right? Whereas 128 is not.
Still not called 3.
That's right. OK. The difference is these are much more common. And when you actually get to resolve the branch, you would like to handle it right away. Because you don't want to wait until the branch becomes the oldest, which may take a long time, depending on how deep your pipeline is. And this becomes much bigger, of course, in an out-of-order machine where you can make this reorder buffer very, very large. OK. You need fast state recovery to minimize the performance impact of mispredictions. So how fast is state recovery? Let's take a look at that. Well, first of all, latency of the state recovery affects multiple things, right? First of all, exception service latency. How fast do you service an exception that's divided by 0, for example? Interrupt service latency. How fast do you switch to another, potentially to service an interrupt that's external, like handling a packet, for example, or the timer interrupt. And latency to supply the correct data to instructions fetched after a branch misprediction. That's really what we're affecting on a branch misprediction, right? Because this data is not correct when we have the branch misprediction. So which ones above need to be fast? And how do the 3 state maintenance methods fare in terms of recovery latency? I guess I'll give you the answers probably. I've already given you the answer, right? This is much more common, so it's likely that this needs to be fast. Whereas exceptions and interrupts, you could argue that they may need to be fast, but it's harder to recover into a state relatively quickly when you get an interrupt. Although with interrupts, you don't have the problem, right? When you get an interrupt, you already have the architectural state in the architectural register file. And you can just flush everything in your pipeline if you really, really need to handle that interrupt right away. Make sense? Whereas with branch mispredictions, it's internal, right? Your internal state is really important. OK. So how do these methods fare? Basically, how do we, the answer depends on what we do when we try to recover the state of a branch. So with a reorder buffer, we need to wait until the branch is the oldest instruction in the machine. And once that happens, we need to flush the entire pipeline. And then we have the correct state in the register file. With a history buffer, well, we need to undo all instructions after the branch by rewinding from the tail of the history buffer until the branch, and by restoring old values one by one into the register file. And we need to flush instructions in the pipeline that are younger than the branch. With a future file, we need to again wait until the branch is the oldest instruction in the machine, copy architectural register file to the future register file, and flush the entire pipeline. The question is, can we do better? Basically, our goal is to restore this front-end state such that the correct next instruction after the branch can execute right away, after the branch misprediction is resolved. Basically, when we get to this branch, when it's mispredicted, regardless of whatever instructions are in the machine, we'd like to be able to restore this front-end state such that the next instruction we fetch at next PC, or the target of the branch, or the correct target of the branch, can execute right away. So how do you do that? Checkpoints. That's good. Exactly. That's the idea of checkpointing. Basically, whenever we fetch this branch, we create a checkpoint of this front-end register file. Now what we have is, with every branch, we know the state of the front-end register file to go back to, right? Let's say this is front-end register file latest. Well, I guess we don't have basically a single front-end register file, but we have multiple of them. And each of them is associated with a branch. The one that we're currently using is the latest checkpoint. The one that's the oldest is the oldest checkpoint belonging to the oldest branch in the machine. Right? And let's say this branch is, let's say we have branch 2 here and branch 3. Let's say branch 3 has the latest checkpoint. And branch 2 is associated with this checkpoint. When we detect a misprediction on this branch, what we do is we start using this front-end register file that's associated with that branch. That way we can quickly go back to the state we had when we fetched that branch. Right? Now it's a little bit more complicated than that, because you need to keep the checkpointed state updated with the results of instructions older than the branch, right? These checkpoints, for example, when you fetch this branch, you create another checkpoint, copy the front-end register file. But these instructions that are older than the branch, they'd better update that checkpoint, because you do want these results to be available to the instructions that are coming after the branch, right? But branch instructions that are coming later than the branch don't update that checkpoint, because that's the whole purpose, right? You need to go back to the state that's here very quickly. OK? And that's the paper that actually introduced it for out-of-order execution machines, but you can employ this in any machine. OK, so how do you do that? When a branch is decoded, we make a copy of this future register file and associate it with the branch. When instruction produces a register value, all future file checkpoints that are younger than the instruction are updated with the value. Basically, when this add, for example, let's make it more interesting perhaps. You have a branch here, branch 1. This is branch 1's checkpoint. This is branch 2's checkpoint. This is branch 3's checkpoint, and this is branch 4's checkpoint, which is the current checkpoint that we're using. This branch 1, and we have an add instruction here, add R2. It's producing the destination. Its destination register is R2. When this instruction executes, it updates all younger checkpoints. It updates checkpoint 2, 3, 4, but it doesn't update checkpoint 1 because that branch was younger. Okay? When a branch misprediction is detected, the action is now simple. We restore the checkpointed future file for the mispredicted branch. Right? Basically, that becomes, let's say, we figure out that this branch is mispredicted, and we have the checkpoint number, it's checkpoint 2. This becomes a current checkpoint. And we deallocate these checkpoints. Basically, we don't use them. Right? So how do you, what does it mean for a checkpoint to become the current checkpoint? Basically, the register file you access, maybe you access all of these in parallel, but the values you get are muxed out in the front end, and you pick the latest checkpoint, or the current checkpoint, the value coming from the current checkpoint when you're decoding the instruction. Right? That's one way of implementing it. Okay? And of course, when a branch misprediction is detected, we flush all of the instructions in the pipeline that are younger than the branch, and we deallocate checkpoints younger than the branch. I already told you that. Okay? That's the idea. It's conceptually simple again. Implementation-wise, well, it could be a lot of overhead, right? Now you have n copies of the future register files. You could potentially make this simpler by only storing those values that change between checkpoints. Right? And people have considered implementations like that. But I'll let you imagine. Yes?
When you deallocate a checkpoint, then this checkpoint is no longer used. So you should become the newest, whatever instruction is the newest one, right?
There.
Because previously the checkpoint is stored, and then now you don't use it, so you just make it like a normal future register file. So how do you do the update? Do you do a large interconnect between every register and just copy from the newest checkpoint? I mean, no, sorry, the newest file?
Wait, I didn't understand that. When you deallocate a checkpoint, you basically change the pointer, right?
To the future, right?
To an earlier one.
Well, to the latest one, because it's no longer being used.
So, okay, this was, let's say this was our current checkpoint,
Right.
branch 4.
Right.
But branch 2 incurred a misprediction. You basically get rid of this, right?
What I mean is, suppose it was correctly predicted. So you
Okay.
no longer need to use that checkpoint anymore, the old checkpoint. So that checkpoint is
Oh, I see. When the branches and everything is correctly
is
predicted.
correctly predicted, right? So the old checkpoint is deallocated.
Okay.
It should be restored to the current checkpoint.
Okay, I see.
Is that correct? Because
No. The front end state is always fine.
Right.
The front end state always looks at the
the
current checkpoint.
Right. So what I'm saying is when the old checkpoint is no longer used, you need to update it to the current state. So you can reuse as a checkpoint for the next instruction.
That's true. Then you deallocate it. That's right.
Right. But
I didn't specify when the checkpoints are deallocated when the branch is correctly predicted.
So when you want to update it, you have to do a copy of every single register.
Why do you need to update it? That's the part. Because you do have an architecture register file in the end, right? That stores your correct states.
So when you want, so when you issue, so when you say you fetch a branch, then you allocate a checkpoint for it, right?
That's it.
That checkpoint has to be the newest state of
That's right.
at that moment.
Exactly.
So every file has to be updated to the newest state.
That's right.
But all checkpoints don't update themselves until they stop being a checkpoint.
Because I don't quite understand that. So when you have that, there's always a checkpoint. There's always one checkpoint in the machine.
So like all checkpoints are frozen really in time, right? So you can fall back to them if you mispredict a branch.
That's right, yes. And there's a checkpoint associated with every branch.
Right. So those checkpoints are not updated to the current state. So when those checkpoints are no longer in use, you need to update them to the current state.
I see. Maybe what you're saying is when there's no branch in the machine.
What?
Yes.
I think what you're saying is like once you deallocate, then the checkpoint is no longer frozen, right?
What does frozen mean?
Like you can't change the registers in the checkpoint because suppose BR2 was correctly predicted correctly, then you deallocate that. But
Yes.
then when you encounter, let's say BR5, then you can put that BR2 checkpoint as a BR5 checkpoint.
That's right. You have an order in between checkpoints, right?
But then you need to update the register file before you can use it as the new checkpoint for BR5.
Yes. Justin, maybe you can clarify this.
How do you copy the entire state from one feature file to another?
You don't need to. You don't need to because, remember, instructions always update the later checkpoints.
Right, but they don't update the earlier checkpoints.
They don't need to update the earlier checkpoints because somebody else is updating the earlier checkpoints, right? They can make this work.
Why would you update the earlier checkpoints? Because that would defeat the purpose of them being a checkpoint, right?
So other instructions, earlier instructions are updating the checkpoint, right? So you always have a the correct state of the checkpoint because checkpoint, the purpose of the checkpoint is you have instructions, at some point, instructions before the checkpoint will have their updates done on the checkpoint, and no other instruction after the checkpoint will update the checkpoint.
But they don't have the values after the checkpoint, right?
Well, you don't need to because there's another.
But when you want to reuse the register file as a checkpoint for another branch, then you need to update them to the current state.
So like, to clarify this question, like, if suppose you deallocated VR2, right?
Okay.
And then after some time, after VR4, you get a VR5.
Okay.
So you need to first copy everything that you have in your current registers into the old VR2 checkpoint, so that it's up to date for the VR.
Oh, I see what you mean. Basically, whenever you create a checkpoint, that's what you're saying. So that's this one, right? When a branch is decoded, make a copy of the future file and associate it with the branch, right?
But how you make the copy? So if you just do
Oh, how do you make the copy? You basically flash copy, right? So one way of implementing this is actually, and that's where the complexity comes from. But one way of implementing this is you have very tightly coupled register files. You flash copy the entire register file to the other register
But
file.
that will make the circuit fairly complex.
Well, that's one of the downsides of checkpointing, right? But that's what. So you're asking this part, right? When a branch is decoded, you make a copy.
Right. So is there possibility to do an incremental copy from your?
That's right. So that's what I was saying with the difference, right? Maybe you don't copy the entire thing and you keep a difference somehow. But then that complicates now the data structures to keep track of this checkpoint. But assume conceptually, don't go into implementation now. Conceptually, you just make a copy and everything works right. So I told you we're having a problem with the conceptual implementation, but conceptual working of this. As long as that works, you always have the correct values. Right? Implementation, now that's a different issue. How do you implement this? Well, one option people have looked at is having flash copies. And in fact, Alpha 21264 has something very similar to this. They call the register maps. It's not really all of the register values, but it's really the register maps, or register alias table that we will see, RAT. The idea is very similar. You still have checkpoints. They don't store the values of the registers, but they store the pointers to the register file, where actually the registers reside. And you basically copy. Whenever you fetch a branch, you copy the previous checkpoint to the current checkpoint. And they do have an implementation of the circuit. And I haven't examined the implementation, but they have implemented this. Yes?
But at some point, you can still run out of the number of seconds.
Yes, then you stall. Then at that point, if you fetch another instruction, you stall. Right? So you design your system such that that stalls are minimized. And I don't know the exact number, but I believe Alpha 21-64, you can read that paper, I believe they had 20 checkpoints or so. Yes?
Would that number be more or less the number of cycles it takes for you to resolve your branch times the frequency of the branches? So you really only need a checkpoint until the branch is resolved, right? And you need a checkpoint for every branch that happens in between this before you can reuse the old checkpoint.
That's right, yes. So yeah, you could make that calculation. That's it.
How good that number
It's not exactly that way, perhaps, but we can take that offline. Okay. Okay, I guess we actually discussed the advantages and disadvantages of checkpoints. We haven't gone into, I'm not going to add more to it, but advantages, fast recovery, right? Enables fast recovery. Disadvantages, now more complexity. You somehow need to deal with all of these issues copying checkpoints, restoring checkpoints. And I'll let you think about what happens when you don't have any branches in the machine, right? You still need some future register file. So you actually need to keep track of the latest checkpoint somehow. You never deallocate the latest checkpoint, basically. OK, anything else? But hopefully you've seen how beautiful this is. So all of these concepts are actually employed today. You do have this checkpoint that exists. I talked about Alpha 21 to 64, and they did checkpoint on branches. In fact, several ideas that have been proposed is you don't checkpoint at every branch, but you checkpoint the register file at every low confidence branch. That reduces how many checkpoints you have here, right? Because the machine is predicting that it's likely that I'm not going to go back to this branch because I've been predicting it correctly. So you checkpoint only on low confidence branches. Then the question is actually, how do you do recovery when you don't have a checkpoint? Well, you go back to the previous checkpoint in that case, right? Or you wait until this branch actually becomes the oldest and then flush the entire pipeline. So there are ways of recovering the state, even if you don't have a checkpoint associated with it. Think about the checkpoint as accelerating recovery. OK. So we've been talking about registers. But memory is different, right? Memory has fundamental differences. And I guess I'll answer this because I'd like to cover some things. We've seen that one fundamental difference is register dependents are known statically, but memory dependents are determined dynamically. And that actually leads to how we handle memory operations differently. Register state is obviously small, memory state is large. We don't want to checkpoint the memory state. You could actually, but that's another. So we don't want to have similar solutions and state updates in memory. That's what this leads to. And register state is not visible. One other fundamental difference is if you have a multiprocessor system, if you have multiple processors operating on the same problem, the register state is not visible to other threads or processors. This is private, right? Whereas memory state is shared between threads of the same process, which means it's shared between different processors in a shared memory multiprocessor. Which means that if you do an update to memory that's out of order, even though it may be OK from the point of view of this particular thread, you may be able to recover it. If some other thread actually uses that value, now you're in trouble perhaps, right? Because you've done an update to memory early on, out of order, out of the program order. If you only consider this thread, you may be able to recover it, right, with it, because you go back to the old value somehow, with a history buffer, for example. But if some other thread already read that value, then it's very difficult to recover the entire system state. Right? So this is another fundamental difference. Whereas registers, you don't have this problem because registers are not shared between different threads. OK? So that leads to a different way of handling memory operations. Well, that leads to basically undoing a memory write is much more difficult than undoing a register write because of the reason that I just told you. So how do we handle out-of-order completion of memory operations? One idea is to keep the store address and data in the reorder buffer and do the updates to memory in order. And that's how existing systems operate, because it's too difficult to handle the case where if you update memory out of program order. And we will see actually other issues related to this when we talk about memory consistency in multiprocessors. Basically, we use the reorder buffer, and memory updates are done. There's only one version of memory, no checkpoints. When a store is the oldest instruction in the machine, it takes its address and the data that's stored in the reorder buffer, and it's completed. Basically, it writes to memory at that point in time. Which means that younger stores that are completed could be sitting in the reorder buffer with their addresses and data. Right. Then the question is what happens if load comes in. Right. If you have a load coming in and it has the same address, you cannot get that value from the cache, right? Or from the memory state, because there is a store in the machine that is not updated that address. Let's say you have store to address X, and it has actually completed. Completed meaning it has its address available and it has its data available, data 1000. Let's say this is your memory state. Let's say this is your data cache. Address X contains 0. This is the old value. This is supposed to be the new value. And you have a load instruction here that wants to access address X. What do? You don't want this load instruction to get 0 to read memory, because there is an earlier store to the same location that is updating that value. Okay? I'll let you think about it, but existing processors are actually quite aggressive in doing that. Right now, assume that loads and stores complete in order. Basically, you can assume that one very conservative way of handling this is ensuring that this load actually doesn't access memory until the store completes. But you see a problem with it. Right now, you're adding additional latency. But OK. So existing processors actually use store or write buffers. These are similar to reorder buffer, but used only for store instructions. Why? Because if you actually store address and data with every single entry in the reorder buffer, that becomes a huge reorder buffer. So existing processors decouple reorder buffer from the store buffer. They still keep the information about the stores, but they also have a special store buffer that contains addresses and data of the stores in order. And this can be much smaller, right? If your reorder buffer size 100, and if only 20% of your instructions are stores, you don't need to store address and data for every every entry. Yes?
Does this have to be common between threads and processes?
Does this have to be common? No, this is just for this single processor.
So what if there's a store to an address in one process and then the load in another one?
That's right. So those are communicated only when the stores here commit. The later stores here are not visible to other processors.
Wait, yeah. So what I'm saying is, like, suppose that store in the middle is in this process, and then that load X is in some other process.
Okay.
So how will that other process know that there's a store pending, so it can't load yet?
I see. Yeah. So we'll get to that. That's right. This is actually that's the cache coherence problem also, right? You need to keep this coherent, just like caches. Yes.
So this means that the CPU already issued the store operation to the MMU until it is the oldest instruction.
That's right. Exactly.
But then the longest time that it takes is really for the MMU to write this to memory. So this is increasing that delay even longer.
That's right. Exactly. But what you can do is actually when you send it to memory, you can actually keep it in the store buffer such that later loads can get it. So you can forward that data. This basically, what I discussed tells you when the store actually updates, makes its update visible to architectural state. You can forward that value with some other data structure here. That's what the store buffer is actually, partly. So what is this? This is a program order list of uncommitted store operations, but they could be also committed. You could keep it until it's written to memory. When the store is decoded, it allocates a store buffer entry. And when store address and data become available, you record them in the store buffer entry. And when the store is the oldest instruction in the pipeline, it updates the memory address cache with the store data. Okay? So in order updates. This does lead to a lot of issues. So you're asking good questions, actually. What happens with multiple processors? You don't want another processor to get the stale value, because this processor is going to store. But one way of handling it is actually when a processor commits its result. You have the store. This is now done. It's storing to address Y, let's say, data 1000. What it does is it sends this value to the cache hierarchy. At that point in time, all caches need to be updated with this value, right? Or maybe that's too strong. any processor that needs to read y after that point in time should get 1,000. And if another processor already has a load to location y, and if it's already read that location, and if it's already got, for example, 0, you need to correct that. How do you correct that? Well, when the store actually writes its result y, it broadcasts its address y, and anybody who's read address y already invalidates its result. This is called snooping, basically. We'll get to this when we cover cache coherence. We're going ahead of ourselves a little bit, but since you asked the question, this store buffer is snooped with the address, or the store load buffer is snooped with the address of the store that's being committed in some other processor. And if the processor already read the same address, if there's already a load that has already that has read the same address, that load gets invalidated. Make sense? That way you ensure correctness. But we will cover this in a lot more detail when we talk about consistency and coherence in multiprocessors. So there is additional complexity. And multiprocessors are actually very interesting, but they do add a lot of complexity. OK. I think I'll stop here for today. Should we stop here? OK, good. This is a good place to break. And we'll start with out-of-order execution next time. But I've already given you the key concepts. And I'll put up these slides so that you can start studying. One of the key concepts for you to remember is the renaming. Right? We can easily link the consumer of the instruction to the producer, consumer of a register to the producer of a register through this ID, through this tag. And once we have that linkage, now the consumer can wait for that tag to be sent out, broadcast, to determine when it can execute, right? To determine when its source is ready. And that's the soul of out-of-order execution. You link the producer to the consumer. Now, instead of the consumer stalling when it sees this val bit to be 0, what it does is you take the consumer out of the way, keep it in a buffer. It waits there. It waits for the producer to send that tag. And when the producer sends that tag, the consumer sees that tag and says, oh, my source is ready. And if all of those sources are ready for a consumer, the consumer can now be executed. And that way you can dispatch these instructions that are waiting. That way you ensure that the instructions that are waiting can get dispatched. And that way you also ensure that instructions that are independent can get executed. Right. That's the idea. So we'll cover that in the next lecture, and maybe the lecture after that too. All right, good luck with your labs, and have a good weekend.